Okay, this is a short YouTube on the scenario of a weight hanging, first of all, from two equal strings, and second of all, from two unequal strings. And so we talked about these in class today. I'm just going over it as an example of a 2D statics problem. So the scenario on the left here is we have two equal length strings. One going to the left and one going to the right, and then some kind of a mass with a downward weight W, I'm going to call, acting down. And so the forces acting on the mass W, on the mass M, which has a weight W, are this tension A up to the left and B up to the left. And then, of course, its weight. And so I can write a Newton number of 2 in the x directions, with this being my axis definition. Minus a cosine theta minus b cosine theta is equal to 0. Both these thetas are the same because the length of the string is the same. And so from that, one concludes that a is equal to b. Since it has to be 0, and since A and B represent the tension force, we'll just let both of them be equal to T. So I have the same tension in both strings, and now a Newton number 2 in the y direction allows me to conclude that the y components, T sine theta plus T sine theta, each one of these now has an upward T sine theta y component. The sum of the two y components minus mg is equal to 0, and so in other words, 2t sine theta is equal to mg, and t is equal to mg divided by 2 sine theta. So one of the implications of this equation for equal strings is that it's impossible to get the string horizontal, because that would involve getting theta equal to 0, and then you'd be dividing by 0, which would require an infinite tension, but any real string would break before that occurred. So you cannot, with any non-zero mass, ever get the string to be horizontal. The second case is one in which the strings are unequal in length, and so here I have a short string drawn as A and a longer string drawn as B, and so I have again a downward weight W here, which I forgot to label, but which I now will, acting down. And so we have a tension A acting on the upwards on the short string on the mass, and then 1B acting this way. And essentially, the only way you can make A and B add together to be A plus B, that will counterbalance this W, it's the same thing I did over here, is to have a longer A along the short string and a shorter B along the longer string. And so if you try this, you will see that this has to be true. In other words, that this has to be bigger than that. So I can conclude simply from doing the vector diagram that the tension on the shorter string is bigger than the tension on the longer string. And so the equations are more complicated. So we have different angles now. We have an angle alpha on the shorter string and beta on the longer string, in which case that would give our Newton number 2 in the x direction minus a cosine alpha plus b cosine beta. That should be a b. I'm sorry, not a beta, but a b cosine beta. B is the magnitude of the tension, and beta is the value of the angle. And then you have a Newton number 2, where the sum of the two y components, a sine b plus, I've done the same thing down here, b sine beta, a sine alpha plus b sine beta minus mg is equal to 0. And so we have two equations with two unknowns. Two unknowns are for a and b, and so one could solve those. We won't in this class. But the important thing to realize here is that from the drawing, one can conclude that the tension in the short string is larger than the tension in the long string.